Okay, yeah. So last time, let's see, I was introducing this reduced Markov chain. So let me just recall that. So we're looking at like comparison of Markov chains so that we'll have two different Markov chains and maybe one is easier to study than the other. And then that will, like if we can relate them in some way, that'll help us study the one that's harder. So we had this set A, which is a subset of our state space, and we defined this induced chain with transition matrix P sub A, and this is defined by saying that P sub A of xy, where x and y are in A, this is going to be the probability if we start our original chain at x, that x sub tau A plus equals y, where tau A plus is the first positive time when the original chain reaches a state in A. So another way of saying this is that like the induced chain on A is just where we run the original Markov chain on A, or on the whole state space X, but then we delete anything that wasn't in A. Okay, and then we have this theorem that I stated and now I'll prove, saying, okay, so let xt for t at least 0 be a reversible Markov chain on X with stationary distribution pi . And spectral gap gamma. And we're going to let A be a non-empty subset of the state space. And let gamma sub A be the spectral gap of the induced chain. Okay, then, so on A. Then the claim is that the spectral gap for the induced chain is greater than or equal to the spectral gap for the original chain. Oh yeah.
Sorry, is this a Markov chain on A or on X?
The original, so this one,
The induced.
the induced one is on A.
Okay.
Yeah. Okay. So proof. Okay, so if we, so I'll just say, okay, by summing over paths, we can find that pi of x, PA of xy equals pi of y pa of yx. Okay, so the point is that like this pa of xy, you could represent as like a sum over paths from x to y in the original Markov chain of various, the probability of going along that path. And if you sum this up and you use the fact that the original Markov chain is reversible, then you can show that this is true. So that this is saying that piece of A itself is reversible with respect to, well, not exactly pi, but sort of the induced version of pi. So let me say what that means. So this is saying piece of A is reversible with respect to pi sub A, which is just going to be basically the conditional distribution of pi conditioned on being an A. So the conditional distribution pi sub A, and this is a probability distribution on A defined by pi sub A of a set B. Well, this should just be the usual pi, oh, sorry. Okay, maybe I want to define this, Yeah, do I want to think of this as, oh, maybe I do want to think of, yeah, I'm a little confused by what I've written here because, okay, so I'm writing this as A intersect B divided by pi of A. Okay, so that would indicate that B is actually a subset of X. And so maybe the answer to your question was that this is a Markov chain on X. Oh, yeah, I think I do want to think of it as, okay, maybe I do want to think of this induced chain as a Markov chain on X. Yeah. Right, okay, so now that's why this makes sense to write this. So now B is just any subset of X. Okay. Okay, so then we had some earlier lemma about, this I think was last time, where we were relating this Dirichlet form to the spectral gap. Okay, so by an earlier lemma, what we had was, so there exists some map phi from A to R with phi, comma, this. So this is the all ones vector, and this is for pi sub A. Okay, but now, okay, I'm confused about whether I want to think of this as on A or on X, because this would indicate that, I'm looking at phi on A. So maybe the point is that like it's on X, but I can just focus my attention on A, because like the induced chain is really just taking place on A. Yeah.
If it's on X, I do not think the statement at the top is true.
Oh.
Because if you take, like, for example, if you take little x not in A, then the right side is 0.
Yeah.
And the left side cannot.
Right.
Can not be
Okay, so then it should be on A, and now I'm wondering why the book wrote, let me see where this is in the book, why it would write, I mean, okay, maybe it should just be the same thing, except B is in A, and then like, okay, A intersect B is just B. Okay, maybe that's what it's supposed to be. I think that's probably right, okay. Yeah, let's just do that. Let's just write it like this. Okay. Here B is contained in A. Okay, yeah, thank you. I think that makes more sense. Okay, so now, okay, so there exists some phi, which is a function on A, such that, okay, so first of all, this is 0, and we can write the spectral gamma sub A as this Dirichlet form, which I'll write as E sub A, so it's just the script E that we had from before, but now it's for this induced chain on A, of the map phi divided by the 2 norm of phi squared. And maybe I'll just specify that this is like L2 with respect to pi sub A. Okay, like the 2 norm, but like on A with respect to this inner product with the pi sub A. Okay, so we're gonna let psi be this map from X to R, and this will be what's called the harmonic extension of phi and it's defined as follows. So psi of X is going to be the expected value if we start the original Markov chain at X of phi of X sub tau A. Okay, let me explain what's going on here. So tau A is the same as tau A plus, except it could be 0. So this is like if you're starting at a point in A, then tau A is going to be 0 because you're already there. And if you start outside of A, then tau A is just the first time that you get into A. So this X of tau A is the first state in the Markov chain that is in A, and you look at phi of it. And so then we're taking the expected value of this given that we start at X. So the reason this is like an extension of phi is because if X is in the set A, this should recover phi of X. Because if X is in X, so maybe I'll just write this out. If X is in A, then what do we get for, so psi of X is the expected value if we start at X of phi of capital X of tau A, but in this case we started at X, so tau sub A is 0, so this is X0, which is little x, so this is just phi of little x. Okay, so that's the sense in which this is extending phi, because it agrees with phi on the set A, but now we can define this on all of x. so now for x in A, what we can write is, well, also, okay, we can look at p psi of x. So what is p psi of x? Well, it's going to be the sum over all states y of p of xy psi of y. And okay, now this is going to be, if we just write out the definition of psi, this is the sum over y in x, p of xy, expected value, if we start at y of phi of capital X of tau A, okay, but now we can think of this as, like, this is the expected value. Okay, so let me write this out. I want to say this is the expected value if we start at x of phi of x tau A plus. Because since x is an A, okay, wait, yeah. If x is an A, then here we're doing like one step of the Markov chain to get to y, and then saying, okay, what is the expected value of phi when we get to A for the first time? But that's like after we've done one step to go to y. So that should be the same as like the expected value of phi when we get to A, like for the first positive time. And okay, where am I using the fact that x is in A actually? Let me just write, if x is not an A, p psi of x is, okay, in this case it's the expected value of phi of x of tau A plus. Okay, so here the point is that, yeah, okay, maybe this is what I want to say. If x is not an A, then when you start at x, tau A is the same as tau A plus, because it's not going to be 0 because you're not starting in A. So then this definition with the tau A should just be the same as, I can make it tau A plus. And then this, okay, this I can say, right, so this is the expected value. Oh, yeah, oh, I see. Yeah, so tau A plus, like this is if I've done one step of the Markov chain so that it's a positive time, but then what I was just saying is that I can replace the tau A plus with tau A. This is the expected value of phi of x tau A. Yeah, because x is not an A. And then this is I should say, okay, up here, what I was writing, this is P A phi of x, right? Yes, so PA phi of x, if you write out what PA phi is, then that's just going to give you the expected value if you start at x. Okay, yeah, so it's this, and then, yeah, I see, okay. And then here, this is psi of x by definition of psi. Yes. Does that make sense? Okay, so what does this mean? I want to look at identity minus p applied to psi of x, and this is 0. Because, okay, so p psi of x is, okay, well, oh, sorry. So, in this case, let me write it here. Yeah, so in this case, we have identity minus p psi of x is 0. Okay. Okay, but now what I want to do is compute this Dirichlet energy, Dirichlet form, sorry, of psi, which by definition was this inner product of I minus p psi comma psi with respect to pi. Okay, and then this should just be, well, it's a sum of I minus p psi of x. So I'm going to sum over x of I minus p psi of x times psi of x pi of x. And I should sum over all of the states except I don't need to sum over the ones that are not in A, because in those cases this term gets 0, so I actually only have to sum over states in A. And then in this case, what do we get? Okay, this is the sum over x in A of, okay, so if x is in A, then I minus p psi of x should be psi of x minus pa phi of x. But oh, the point is that yeah, so I can write this as I minus pa phi of x pi of x, because if x is in A, then psi and phi agree. So psi of x is the same as phi of x, and so then like this is like psi of x minus p psi of x, which is the same as phi of x minus pa phi of x. Okay. So okay, I'm just using the fact that psi and phi agree on the set A. And then, okay, this I can write as, if I use the definition of pi sub A, so I'll write this as pi of A sum over x in A of I minus P sub A, phi of x, phi of x, pi sub A of x. So it's the same thing, it's just I'm replacing the pi of x with pi sub A of x times pi of A, just using the definition here. And then this is just, okay, so I still have my pi of A out front, but this is exactly this E sub A of phi. Right, it's like, it's the same kind of thing, but now on A and with phi. Okay, but then also, okay, one other thing. So let's let psi bar be the expected value of psi with respect to pi. Okay. So just the sum over all states x of psi of x, pi of x. And we're going to let f be psi minus psi bar. Okay, so I'm just taking psi and I'm sort of normalizing it by subtracting away its mean. So if we do this, then if we take the 2 norm of f squared, okay, this is the sum over x in x of psi of x minus psi bar squared pi of x, just by the definition of the 2 norms squared. Maybe I'll write this sign better. And this is greater than or equal to, okay, let me write this as the sum over x in A of phi of x minus psi bar squared pi of x. Okay, so all I'm doing is saying that these terms are non-negative, so if I just only sum over the states in A, then that's going to be less than or equal to this. But when I sum over states in A, I can say that psi of x is the same as phi of x. Okay. And this, this I can write as sum over x in A of phi of x squared plus psi bar squared pi of x. So why is that? Well, I expand the square, I get a phi of x squared, I get a psi bar squared, but then I have like a minus 2 psi bar phi of x, but when I sum that, I should get 0 because we chose this, we have this assumption on phi. This assumption that, like this is just saying, the sum, like the expected value of phi with respect to pi a should be 0, so that ends up giving us a term of 0 when we write this out. Yes?
Why is there an inequality here?
Oh, because I took the sum over all of x, and then I just said restrict it to a.
Oh, okay.
Yeah,
Sorry.
Yeah, no worries. Okay, and then finally, this I can say is greater than or equal to the sum, okay, let me write it as pi of a sum over x in a of phi of x squared pi a of x. Okay, so here I'm saying that pi of x is the same as pi of a times pi a of x. And I'm just getting rid of this psi bar squared term because, you know, I can just delete it and I get something smaller. So I have this now. So therefore, or do I want to say, yeah, okay, so therefore, if we take gamma, the spectral gap for the entire chain, this is equal to E of f over the 2 norm of f squared, which is the same as E of psi over the 2 norm squared, because if you shift, okay, so maybe like if you go back to the definition, you'll see that if you shift your function by a constant, which is what we're doing here, we're just like f and psi are the same up to an additive constant, that doesn't change this form. So this ends up being the same thing. And then this, I'll say, is less than or equal to pi of a EA of phi. Okay, so that, and then, okay, I'll do over pi of a this. Okay, so here, for the numerator, I said, where's E of psi? Yeah, E of psi is equal to pi of a EA of phi, so that's exactly this. And then for the denominator, we're saying the 2 norm of f squared is greater than or equal to this, which, okay, this is exactly pi of a, and then this thing is this 2 norm squared of phi with respect to pi a. So then I'm just plugging that in here, and I get this inequality, and then the pi of a's will cancel, and then this EA of phi over this thing is equal to gamma sub a because of this. Yep. Okay, and that's what we wanted. Yep.
It doesn't really matter, but just checking this first equality should be a less than or equal to, right? Because we don't know that f is the function that minimizes.
Oh, where?
Like gamma is
Oh,
the minimum over possible. Do we know that this is the f that minimizes like this function?
Yes, oh, you're right. Yeah, I have that written in. Yeah, thank you. Yep, good point. Okay, so I guess the punchline here is that this gives us a way of bounding the spectral gap gamma that we might care about from above by restricting to an induced chain that might be easier to look at. So, okay, here's an example, sort of a simple example. Okay, let's consider a simple random walk on a graph. Let's assume this is a d-regular graph. So every vertex has degree d. So the stationary distribution is uniform because it's regular. Okay, so let's choose some vertices, let's say distinct vertices, A and B, and we're just going to let our set capital A be these two vertices. So let capital A be the set A comma B. Okay, then, okay, what is p sub A? Well, this is just a 2 by 2 matrix, and it's going to be, so let me write it and then I'll say what this is. 1 minus p, 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 1 minus p. Okay, what is p? P is just the probability if you start the random walk at A that tau B is less than tau A plus. Right, so if you start at A, then P is like, okay, you run the big random walk on the whole graph, and you want to know, this is like the first time that you reach B, and this is the first time that you reach A, like after you're starting at A, but you want to know like what's the first positive time that you reach A. And this is just saying that B, if tau B is less than tau A plus, that means that in the induced chain, you've transitioned from A to B, and if it was the reverse, then you would just stay at A. So 1 minus P is the probability of staying at A in the induced chain, and then P is the probability of going from A to B, and similarly P is, well, okay, just, you can reverse it and you get that this, the probability of going from B to A is also P, and the probability of staying at B is 1 minus P. Okay, therefore, whatever the spectral gap gamma is for this d-regular graph, it's going to be less than or equal to gamma sub A, and you can compute this because this is a 2 by 2 matrix, and you can just like write out what are the eigenvalues, and this ends up being 2p. Okay, so just some simple application where you might have some complicated graph, but if you pick just two distinct vertices, you can easily compute some upper bound for the spectral gap. Okay, so here's a lemma that could be used to bound gamma from below. Okay, so I'm going to let P and P bar be reversible transition matrices. with stationary distributions pi and pi bar, respectively. If E bar of F, okay, so this is the Dirichlet, E bar is the Dirichlet form, for P bar. If this is less than or equal to some alpha times the Dirichlet form for F, if this is true for all F, then gamma bar, so gamma bar is the spectral gap for P bar. This is going to be less than or equal to the max over x in x of pi of x divided by pi bar of x alpha gamma. I think I won't prove this, but okay, it's just a useful lemma to keep in mind. Okay, so this is like another example where we might have two Markov chains and maybe we can bound gamma from below if we understand something about gamma bar. Okay, I also want to state another theorem that I won't prove, but I'll give I guess I didn't want to get too much into the weeds of just proving a bunch of these theorems because it takes too long and we only have a few more classes. I think maybe 4 more after this if we take into account the presentations. So, okay, but let me go on to this next theorem. So I'm gonna let E be the set of edges in our transition matrix. So this is the set of pairs x, y, or sorry, in the transition diagram. So P of x, y is positive. And we'll define an E path. Okay, so this is just basically a path in this transition diagram using these edges in E. Okay, but an E path from a state X to a state Y is a sequence gamma. So gamma will be edges E1 through EM. So of edges in E such that so E1 it starts at X and goes to some X1, and then E2 goes from X1 to some X2, and so on until eventually EM goes from Xm minus 1 to Y. Okay, so for some X1 through Xm minus 1 in X. Okay, so it's just a path from x to y in the transition diagram. And we're gonna use the notation like absolute value of gamma for the number of edges used, so that in this case is m. And as usual from before, we have this q notation. So as usual, q of xy is going to be pi of x, p of xy. So let's say I have two reversible transition matrices, P and P tilde, be two reversible transition matrices on X with stationary distributions pi and pi tilde. Respectively. Okay, now suppose that for each edge xy in E tilde, there is an E path from X to Y. And I'm just going to choose one. So choose one to denote by gamma sub xy. Okay, and then maybe I'll go over to the next board. Okay, so then we're going to define the congestion ratio B. So B is going to be the max over all edges E of 1 over Q of E. Okay, so by Q of E, I mean, like E is some x comma y, so it's this Q of x, y from before. And then I take the sum over all x and y such that gamma xy includes E. Okay, so So I'm summing, like I have these special paths gamma x, y. And I want to choose, or I want to sum over x, y such that gamma x, y includes this edge this edge E of q tilde of x, y, and then the number of edges in gamma x, y. Okay, so kind of a weird definition, or a little bit complicated, but let me say what the theorem is, and then so I'm not going to prove the theorem, because I don't want to, but there's a corollary, and I'll prove the corollary assuming the theorem, and then we'll give a sort of special case when we're looking at random walks on groups. Okay, so the theorem says for all functions f from x to r, we have E tilde of f. Okay, so this is the Dirichlet form for P tilde. This is less than or equal to this congestion ratio B times the Dirichlet form of f. Okay, and then consequently, yeah. Also, gamma tilde, so the spectral gap for P tilde, is less than or equal to the max over x in x, pi of x over pi tilde of x, B gamma. Okay, so let me give a corollary of this, and I'll prove the corollary assuming this, and then we'll give a special case. Let P be a reversible transition matrix. And let gamma xy be an E path for each pair of states xy. So just for any two states, I find some path from x to y, and I call it gamma sub xy. And let B, so this ends up being the congestion ratio, this is going to be the max over edges E of 1 over Q of E, sum over x and y, such that gamma xy contains E of pi of x, pi of y, size of gamma xy. Oh wait, then the spectral gap gamma is at least 1 over b. Let me add that, I forgot to write that down. Okay, so let me prove this, assuming the theorem. Okay, let's define this p tilde of xy to just be pi of y. Okay, so this is a transition matrix of a Markov chain, but it's kind of weird. It's just saying, like, for any state x, if you're sitting there, then you transition to some pi of y with probability the stationary distribution of y, for where this is stationary for p. And note that, okay, so this is a Markov chain, and its stationary distribution is also pi. So note that the stationary distribution of pi, or sorry, of p tilde is, well, also pi. Okay, so for a function f from x to r with e pi of f equals okay, so this is just this, and let's assume this is 0. We have a function whose expected value with respect to pi is 0. Then we have e tilde of f is, okay, I think we had a formula at one point saying that this should be equal to 1/2 the sum over x and y of f of x minus f of y squared pi of x pi of y. I think probably this is a lemma, maybe last time. And this is also the 2 norm of f squared. Yes. Okay, just because, yeah, okay. The reason it's the 2 norm of f squared is because you expand this out. If you take the sum over x, y of, like, the linear term with f of x, f of y, pi of x, pi of y, that becomes 0 because of this assumption. So this is really the sum of f of x squared, pi of x, plus f of y, or yeah, f of x squared plus f of y squared, pi of x, pi of y, and then you sum that up and you end up getting this. But then, okay, if we apply the theorem, shows that e E of f, okay, so E of f is at least E inverse times this, so times E tilde of f, which is the 2 norm of f squared. And then we had a lemma saying that gamma is the minimum over functions f in R to the x with f comma 1 sub pi equals 0 and f not identically 0 of this E of f over the 2 norm of f squared. And so if you use that, you get that gamma, right, so you divide this by the 2 norm of f squared and you get that gamma is at least B inverse. Yeah, so you take the f that minimizes this, and so then that is gamma, and it's at least B inverse. Okay, let's do an application to random walks on groups. Okay, so suppose P and P tilde are random walks on a group G. Driven by some measures mu and mu tilde. And I'm going to let S and S tilde be the supports of mu and mu tilde. Okay, now for each element A in the support of mu tilde, so for each A in S tilde, let's fix an expression for A written as a product of things in S. So okay, I guess I'm going to assume that the supports here generate the group. So in particular, S generates the group, meaning I can write A as a product of elements of S. So I'll fix an expression A equals S1 through SK, where these are in S. And I'm going to let in of SA be the number of times S. So here S is going to be an element of capital S, and I want to know just how many times does it appear in this expression that we've chosen for A. So the number of times S appears in S1 through Sk. And I'm also going to let, if I write like absolute A, that'll just be the this K, it'll just be the number of generators in this expression. And this is also the same as the sum over S in S of n of Sa. So, okay, I want to write what is the congestion ratio in this case. I don't know, well, maybe I'll have time to go through this, but we can at least start. Congestion ratio in this case is, so it's this B, and it's the max over S in S of 1 over mu of S sum over A in S tilde of mu tilde A in of SA size of, by size of A, then that's this. Yeah, let me see how far I can get with this. So, proof. Okay, we're going to let P and P tilde be the transition matrices, like before. And we're going to have E and E tilde are like the edges. Right, so let E be the set of edges G comma H, such that the probability of going from G to H is positive, and similarly E tilde is the set of GH such that the probability in P tilde of G comma H is positive. Okay, and then for an edge E in capital E, what is our Q of E? Q of E is, okay, this is Q of, so okay, let's say for some edge E, which is G comma H, Q of E, okay, this is Q of G comma H, this is just the probability of going from G to H divided by the size of the group, because, right, this is supposed to be the stationary probability times P of G comma H, but the stationary probability is uniform on the group, so the probability of G is just 1 over the size of the group. And then this P of G comma H is mu of G inverse H over the size of the group, just because of how the random walk on the group is defined. Okay, and then similarly for E tilde, so similarly for E equals GH tilde, if I look at Q tilde of E, this should be mu tilde of G inverse H over the size of the group. Okay, now, okay, so for an edge BC in E tilde, so okay, we have some edge B on the C, and we can write C as BA, where A is in S tilde. Okay, so that's what it means to be an edge in E tilde. And use the expression A equals S1 through Sk that we've chosen to write B equals, or sorry, C equals B times S1 through Sk. Okay, so this gives our E path, so this gives the E path gamma sub BC, where, okay, the path is just, you go from B to BS1 to BS1S2 to BS1S2S3 and so on until you get to C. Okay, and then maybe I'm basically out of time, so let me next time go into the how to compute the congestion ratio. So I guess I'll recap this next time. Okay.